Hi, we should mention a note about our simulations and the Central Limit Theorem. In this series, we've looked at measurement errors, the difference between a measured result and the true value of the quantity we're measuring. Let's say we make a measurement of some quantity. We get a result which we call Q measured. Due to various sources of error, Q measured will differ from the quantity's true value, which we call Q true. Here we are representing the various sources of error by little yellow arrows. We wanted to get a feel for how Q measured would differ from Q true, so we did some simulations. We'll recap those simulations here, and that will set us up for a quick discussion of the Central Limit Theorem. First, we tried simulating the difference between Q measured and Q true as a sum of n error sources, all of the exact same size, but with random signs. This was not a realistic model of measurement errors, just a starting point to lay some groundwork for more realistic models. So the next thing we tried was to have a random walk that took n steps of varying step size, but where the n steps were the same size on average. The step size was randomly chosen from a flat distribution between 0 and 1, and the sign was randomly chosen to be positive or negative. We looked at the cases of n equals 1, 2, 3, and 5 steps. Here we show an example random walk for n equals 5. The individual steps have different sizes and directions, but the sizes are all randomly chosen from the same flat distribution between 0 and 1. We saw that the distribution of ending locations of the random walk looked more like a Gaussian distribution as we increased the number of steps, n. The case for n equals 5 steps looks pretty Gaussian. Even the n equals 3 case looks pretty Gaussian within the limits of the statistics of our simulations. Simulations run with much higher statistics can be directly compared with the Gaussian curves shown in red. The similarity is clear. We then applied these results to an example involving the rounding error on the measured masses of packages. In this scenario, we had a shipment of n packages, their masses adding up to give the total mass of the shipment. Each package's mass was measured, and it had a rounding error, which we took to be by far the largest source of error. The rounding errors on the individual packages sum to give an error on the mass of the whole shipment of n packages. We took the rounding error on the mass of a single package to be flatly distributed between minus 0.5 kilograms and plus 0.5 kilograms. Then the n steps in our random walk corresponded to the errors on the masses of the n packages, up to a scaling factor of 0.5 kilograms. So we could translate the random walk simulation results into a distribution of error on the mass of the total shipment. And we saw a nice Gaussian-like shape for n equals 5 and a slightly less Gaussian-looking shape for n equals 3. But this rounding error example was a very special case. In most real-life measurements, we don't have a bunch of sources of error all of exactly the same average size dominating the total error. So we needed to make a model of measurement errors that was a bit closer to reality. So next, we looked at a simulation where the steps did not all have the same average size. This time, we always had n equals 5 steps for all runs. We still kept the step size flatly distributed between 0 and a maximum step size, but that maximum step size was no longer always 1. So here we see an example path for the case where the maximum step sizes were chosen to be 2, 2, 0.5, 0.25, and 0.25 respectively. we can see that the first two steps did turn out to be much larger than the others, which is not surprising. We compared random walks with different maximum sizes for the 5 steps, starting with the case where all 5 steps had the same maximum size, and moving to the case where one of the steps had a maximum size much greater than those of the rest. And we saw the Gaussian behavior that we had seen before break down. When 1 or 2 steps were, on average, much larger than the rest, the ending distribution was much less Gaussian looking. We then applied these results to a scenario involving rounding error, albeit a scenario a bit more complicated than what we did before. We looked at a case of looking for a rare element in samples of 5 different minerals. We had 5 samples, each of a different mineral, and the measured mass of each of these samples had an associated rounding error. Similar to what we did before, we took the rounding error on the mass of each mineral to be flatly distributed between minus 0.5 kilograms and plus 0.5 kilograms. But this time, each mineral had a different concentration of the rare element that we were looking for. We wanted the error on the amount of the rare element in each of the 5 mineral samples. So we had to scale the rounding error on the mass of each sample by the concentration of the rare element for that sample. To get the error distribution for the total amount of the rare element, we add the errors from the 5 different mineral samples. We can get this final error distribution from our random walk simulation. Each of the 5 steps corresponds to the error on the amount of the rare element from one of the 5 samples. So we could take our random walk results and relabel the x-axis. We saw in our random walk simulations that when 1 or 2 steps had much larger typical sizes than the rest, Gaussian-like behavior was lost. We can translate those results to our example here, finding that when 1 or 2 rounding error sources dominate, Gaussian-like behavior in the total error is lost. Okay, what we observed from these 2 simulations. In the first simulation, we saw that if we had more sources of error with similar typical sizes, the more Gaussian-like the resulting error distribution looked. In the second, we saw that when 1 or 2 error sources had typical sizes much larger than the others, that Gaussian behavior was lost. But we should ask a question about our examples. In both cases, we looked at rounding error, and we took the rounding errors to be flatly distributed between 2 endpoints. The errors were between minus 0.5 kilograms and plus 0.5 kilograms for the first scenario, and for the second we did the same thing, but we also multiplied by a scaling factor. This is reasonable for rounding error, but a rounding error is a particularly convenient example. What about other types of errors? What about statistical errors, errors from noise, temperature effects, errors from calibration of measuring equipment, errors caused by vibrations, and so on? These errors are likely not flatly distributed between 2 endpoints. Do our conclusions about a Gaussian-like error distribution still hold? Okay, so we need to talk about the Central Limit Theorem. There are a few versions of the Central Limit Theorem, and their discussions can get pretty technical. So we're not going to get into the specifics, but instead we'll just talk about the relevance of the Central Limit Theorem to our results here. Here's the basic idea. under some reasonable conditions, as the number of error sources becomes large, in other words, as n goes to infinity, the shape of the error distribution will become more and more Gaussian-like. The central limit theorem does not require individual error sources to have flat distributions within a given range, like we had here. And there exist forms of the central limit theorem where the distributions from different error sources do not have to be the same. The most common formulations require that the different error sources be independent, which ours were. So what this means for us is this. It tells us that approximately Gaussian-like behavior will arise in the distributions of measurement error for a wide variety of situations, as long as the number of sources of error is large. This behavior, at least as a reasonable approximation, comes up often. What it doesn't mean. It does not tell us how good the Gaussian description of measurement errors is for a specific situation, and it doesn't tell you if approximating the error distribution as Gaussian will be good enough for your case. We can look back at the error distributions for our second rounding error example. When all of the error sources had the same typical size, the resemblance of the error distribution to a Gaussian, at least to the eye, was clear. When one source dominated, the Gaussian description failed badly. And all of these plots were made for n equals 5, so the number of error sources alone isn't enough to tell you if the Gaussian description is a good one. So we shouldn't be surprised if Gaussian-like behavior arises in the distribution of measurement errors, but it's also not guaranteed. Also, we need to keep in mind that the Gaussian description of measurement errors is always an approximation. Sometimes it is an excellent approximation. But if a specific situation requires a very precise description of the error distribution, then dedicated studies, including calculations and/or simulations, should be done. With that, let's look at a very useful special case. Let's say we have a scenario where there are n equals 2 important independent sources of error. And those error sources, of course, fluctuate from trial to trial. Now, 2 is not a large number, so we might think our simulations and the central limit theorem don't help us here. It seems like we can't say anything about whether or not the error distribution would be Gaussian-like. But if both of the individual error sources are Gaussian distributed, the total error will be 2. Is this just an impractical special case? Nope. The two error sources may themselves be composed of many smaller independent sources of error. Let's look back at our package shipment example. Let's say Monday's shipment this week had 5 packages, and Tuesday's did as well. We want to know the error distribution for the mass of the total of the shipments over those 2 days. We can look at the total error as the sum of the error on the mass of Monday's shipment and the error of the mass of Tuesday's. From this perspective, there are n equals 2 sources of error. We know the error distribution for the mass of Monday's shipment. It was the nice, almost Gaussian-looking plot. And we know the error distribution for the mass of Tuesday's shipment. It's the same plot. We saw this Gaussian-looking behavior emerge from the sum of 5 independent errors, all of the same average size. Since the total error is the sum of 2 independent errors, which are both approximately Gaussian distributed, the total error will also be approximately Gaussian distributed. In fact, in this case, we would get the same result as if we had had a single shipment of 10 packages. Furthermore, if we have n independent error sources, each of which is Gaussian distributed, the total error will also be Gaussian distributed. And this holds even if the Gaussian distributed error sources have very different typical sizes, and also even if n isn't very large. This can happen in real-life measurements. Statistical errors are often, but not always, approximately Gaussian distributed. If your measurement apparatus has electrical noise in many different components, and the noise in each component is independent of the noise in the others, the total error induced by electrical noise may be approximately Gaussian distributed. Similarly, your measurement apparatus may be affected by background electromagnetic radiation, which comes from many independent sources. So it's very possible for individual sources of error to be approximately Gaussian distributed. And this means that even if just one source, for example, statistical error, dominates, it is still possible to have Gaussian-like errors. Okay, let's get to the main point. In this series, we've tried to understand when measurement errors are approximately Gaussian distributed. And to do that, we did some simulations. We looked at two examples, both of which involved rounding error. But rounding error is too simplistic to be a realistic model of measurement error for most scenarios. But thanks to the Central Limit Theorem and the fact that sources of error are often composed of many smaller sources of error, we can say the following. The Gaussian behavior we saw in our simulations arises, at least approximately, in a much wider range of scenarios than our simulations demonstrated. Gaussian behavior is not guaranteed to happen in a specific situation, but it arises, at least approximately, quite often. And that's why it's so important to understand Gaussian errors.